We can make a lot better multimodal large language models by using reinforcement learning. So the vision part of the multimodal large language model sees better, understands images better than if we use supervised fine-tuning. Even though this is very often used, this doesn't make the model understand vision as good as reinforcement learning does and understand the images, what it's looking, what's the details, and which parts of the image it needs to take or look at or pay attention to answer the question. And so this paper provides a very good overview of the findings and how to improve your vision language models, multimodal language models, etc. The core difference is that supervised fine-tuning just teaches the model to imitate data to roughly understand what text belongs to what kind of image, the description, but reinforcement learning makes it look for details, understand why some question is wrong, why some question is right, the answer, and find evidence on the image to show that if this answer is correct or wrong and why. So you see this image, and the question is, what is the woman with the coat holding in her hand? And so there is just woman in the coat here, and supervised fine-tuning would pay attention to a bunch of different parts of the image, but reinforcement learning, direct policy preference optimization, would just pay attention to these hands of the woman. The issue with the current multimodal LLM training is they are, first of all, mostly focused on the text part, and the vision part is a lot less understood. So, for example, there is no deep research on if supervised fine-tuning performs better than reinforcement learning or not. It's also unclear why reinforcement learning helps multimodal LLMs. Is it because it improves text generation or improves the vision parts themselves? They have a few findings from their experiments. So they use SIGLIP as the vision encoder and Qwen 2.5 as the LLM. So SIGLIP 2 is the vision part, and first they find that on complex tasks it helps to scale the vision encoder to make it bigger. For tasks that include reading text from images, answering questions from charts, and then other vision-related questions that are about analyzing the image with vision. And reinforcement learning, direct preference optimization, consistently outperforms supervised fine-tuning, especially on vision-heavy tasks. So if the vision is not so crucial for the answer, if text is more important, then they perform kind of similarly. But the more details you need to understand from an image, the better reinforcement learning, DPO, performs. These are the reasons and hypotheses on why reinforcement learning is better. So in supervised fine-tuning, you just give it image of a person and say this is person on the street. But in reinforcement learning, you would give it same image and then maybe correct answer and the wrong answer. And now the model needs to learn what makes answer correct, what makes answer wrong. While the supervised fine-tuning just repeated whatever the text it saw. So it needs to think about the image a lot less. And so supervised fine-tuning is not penalized for not understanding small details or differences between a wrong and correct answer. It just tries to imitate as much as possible to be more like the correct answer. And DPO is trying to maximize the probability of the correct answer while minimizing probability of the wrong answer. So it's looking for visual evidence on the image that supports the correct answer. It's correlating visual evidence with the correct answer and also correlating visual evidence with the wrong answer and why it's wrong. And look at this. The question is, are there curtains on the window? And so the supervised fine-tuning will actually pay attention of it will be a lot more scattered everywhere around, while the reinforcement learning, DPO, just focuses on the window and understands that this is the evidence it needs. Are there curtains or not? So it looks like it's more focused, it's more precise, it knows what to look for on the image and understands the image more. Then researchers also detached the vision encoder from the multimodal LLM to test its standalone visual capabilities. And the third thing here they found is that when it's trained, and because it's trained with language, it changes. So the language itself changes the vision encoder and how it processes images. So when you train the entire multimodal LLM from beginning to the end to end, and allow the vision part to change as well. The language model will change it. So in the beginning, it may just be able to correlate images and text description of that image, but after the training, it also learns to scan the image for visual evidence to answer text questions. It learns to prioritize features or parts of the image that are crucial for answering the text question. It can even learn to pay more attention, for example, expression of the human face, as opposed to just knowing that this is a human face, this is a human, just correlating description with the image. And they tested this new SIGLIP2 trained vision encoder versus the original that was not trained additionally with the LLM. And they found that this new performs a lot better on this task that they measured of classifying ImageNet images. So it became smarter and more generalizable and understood more concepts. So the original one may look at an image and say, car, person, building, road. And the new one may have a lot more understanding, like blue car next to a person wearing a red hat in front of a brick building with the number 24 on it. And this all comes off of this training together with the large language model to be able to understand the image better and provide visual evidence for answering the LLM questions. And also, the vision encoder benefits from a larger LLM, because larger LLM will have more understanding. It will provide better gradients that describe more things. And based on all of their findings, they developed this pivot recipe or framework for training a good vision, a multimodal large language model, and the vision part. So you would start with already good vision encoder like SIGLIP, Dino, Clip, and Mae. Then you can attach moderately sized LLM like Qwen 2.5, 1.5 billion parameters. It doesn't need to be state of the art, it's just a teacher for this vision encoder. Then you train this on just standard instruction following with vision tasks. This aligns, this will kind of merge the LLM and the vision models and make them learn to work together. Because the way architecture works is vision model generates a token, and then there is like a neural network layer that converts the vision token from vision language model to the large language model token. It's like glued with this layer. So you need to train them together so they start to understand and communicate the same things, start to understand each other, and be able to convert tokens and communicate properly. And then you use reinforcement learning, DPO, with the pairs of good-bad answers, which will give all of the benefits that we described. And then, if you want, you can throw away the LLM and just keep the now a lot smarter vision encoder model like SIGLIP or Dino. So that's gonna be it for this video. Join my school to become AI researcher. We have all of these courses. It's currently free, but I'm gonna make it paid soon, so hurry up. Link below the video. See you in the next one.